Hello there. This lecture is all about correlation, which is probably the most commonly heard type of experimental design and statistical analysis. A lot of people talk about correlation. There's a correlation between this and this, but few people actually understand what it means and what are the limitations of correlation. So thus far, we've been examining whether an independent variable has an impact on a dependent variable by examining the difference between a sample mean and the corresponding population mean. So that's where we started, looking at Z or single sample t-tests. We also examined whether an independent variable has an impact on a dependent variable by looking at the differences between sample means, or, the sample mean scores, to infer the differences among the corresponding population means. So that's when we did the related independent measures t-test in ANOVA. So we were just looking to see if the differences in the dependent variable were based on either the manipulation of the independent variable or by grouping individuals based on their level of the independent variable, or, a quasi-independent variable. So we were looking at differences between different groups, and those different groups were differentiated based on their level of the independent variable. And then we were measuring the dependent variable to identify if differences actually existed between those groups. Well, now, instead of focusing on examining the differences in the dependent variable between groups or samples who are differentiated based on the independent variable, we're focusing on examining the relationship between two variables measured in the same sample. So with correlation, we aren't really manipulating anything. We're just doing a natural observation or measurement of how two variables co-occur naturally. We're not manipulating anything, again. We're just measuring two different variables in a single group to see how those two things are related. Now, one problem with that is that the independent variable and the dependent variable are not always explicit. You don't always know which comes first and which comes second, which caused the other or which predicts the other. So we usually do have some sort of preconceived notion of what our independent variable is based on past research. And sometimes when you are doing a correlation, you know what comes first. So for example, if you're looking at the relationship between the number of siblings you had growing up and the number of children that you eventually have. Well, the first thing that happened to you was how many siblings that you had. You know that comes first. But even so, you don't know that if there's a relationship that having those number of siblings caused how many children that you have. And we'll talk about how correlation doesn't equal causation here in a minute. But for right now, just keep in mind that the independent variable and the dependent variable aren't always explicit. You don't always know which one is which. But we usually assign the variable that's called the independent variable, or that we think may be the independent variable. We label that as X. And then the variable that we think is probably the dependent variable in this relationship, we label that as Y. So X and Y. So although we may not know which variable is the independent variable and which is the dependent variable, we're mainly examining whether or not the two variables, X and Y, are related. And the term related just says there's a consistent pattern among scores on two variables, such that higher or lower scores on variable X are consistently related to higher or lower scores on variable Y for each participant. So it's just kind of an overall lowdown of what correlation is. And we'll get into the nitty-gritty of every little piece of it here in a minute. So first I'm going to talk about the three characteristics of relationships. And basically, the reasoning for that is that there's something called the correlation coefficient, which gives you information about the characteristics of the relationships. Then I'll get into the steps of a hypothesis test with correlation. As always, step 1 is stating your hypothesis. Step 2 is finding your critical value, or the cutoff for significant findings. Step 3, calculating your test statistic. And step 4, making your decision by comparing what you calculate in step 3 to the critical value in step 2, and then stating your conclusion. So the steps haven't changed. It's just the details that have and how you do those steps. Then I'll show you a couple examples of a hypothesis test using correlation. And then I'll get into all the reasons, well, just some of the main reasons, why correlation does not equal causation. Just because you find a significant relationship doesn't mean that X caused Y. So the first characteristic of relationships that I want to talk about is form. So in other words, if you plot data points out in a scatter plot where x-axis represents values for the independent variable and the y-axis, or the vertical axis, represents the values for y, the dependent variable, or the pseudo-dependent variable, what you think the dependent variable is, when you plot those out, you'll start to see a shape in your data. And that's what form is all about. And one thing I want to mention about scatter plots too is that before, whenever we were plotting out data, we were using histograms or bar graphs. Well, that's when we have a frequency distribution, where the x-axis is the values of the variable that's being measured, and then the y-axis are the frequencies. Well, in this case, x again represents what you think the independent variable is, the x-axis. The y-axis represents the values for what you think the dependent variable is, the y variable. And so you're having two different variables plotted on the same graph. Whereas before, with the frequency distribution graphs, you had one variable plotted on a single graph, and the height of the bars, for instance, represented the frequencies. Well, in a scatter graph, you're going to have dots, and each dot represents one person and what their level of x and y are. And I'll show you plenty of examples of that. So when you do this scatter plot, you'll see some sort of form emerge. And if you don't see any clear pattern, then that is a pretty good sign that there's no relationship between x and y. So if you just see kind of like a shotgun effect of dots all over the graph, then that's probably a good sign, again, that there isn't a consistent relationship between x and y. If there is a relationship between x and y, your independent and dependent variable, or what you think your independent and dependent variable are, there's really two major types of form that you can have. One is curvilinear, and I'll show you a couple examples of a curvilinear relationship. Curvilinear just means that it isn't a consistent increase or decrease in y for an increase or decrease in x. When you have a curvilinear relationship, the type of data analysis or correlation that you would want to use is the Spearman correlation. We aren't going to talk about that, but I will show you what a curvilinear relationship is, and you can read about the Spearman correlation in your book. What we're really going to focus on in this lecture are linear relationships. So when there is a consistent increase or decrease in y for all the increases or decreases in x across all the participants in your study. And we're also going to be focusing on the Pearson correlation, or the abbreviation for the Pearson correlation is R. So here's an example of a curvilinear relationship. So this is a very well studied relationship between stress and performance at work. So let's say that you have a sample of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 people. Remember, each dot represents one person. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 dots. And when you're counting participants, keep in mind each person is measured on both x and y. So each row represents one person. And just to really show you how the scatter plot works, just in case you aren't familiar with it, for instance, the first person had a 0 on x and a 50 on y. X, 0, 50, y, boom. That dot represents that person. So I hope that makes sense. So what this curvilinear relationship indicates, and you can look at this, I made this example pretty clear. As stress increases, so as people's value of x tends to increase, you see, okay, starting at the bottom, well, their performance is actually increasing as stress increases. And then it reaches this plateau of really high performance, and then it starts to decrease or go down. So in the industrial organizational psychology literature, you'll often find that in very, very low stress situations, there's not a whole lot of motivating factors for people to perform. They become complacent. There's nothing stressing them out or getting them interested in doing work tasks because there's some sort of consequences for not doing so. So their performance is low in really low stress situations. But then in really high stress situations, they're just overloaded, or maybe they have conflicting instructions being given to them and it's really stressful and they don't know what to do, or they just got too much going on. They're just overwhelmed and they're stressed out and they can't perform. So then performance would be low in that case. But in the middle, there's like this moderate level of stress. It's kind of like the sweet spot where there's just enough stress to motivate you, but not too much so that you can't perform anymore. So if you looked at this relationship with Pearson's correlation, which is designed for linear relationships, not curvilinear, it would be misleading. Here's another curvilinear relationship, or a U-shaped curvilinear form. So we're all probably pretty familiar with this. You know, as you get, well, when you first start driving, your insurance premium is really high. And most of us start driving at least by age 18. So your insurance is really high because they think you are a huge risk, right? You're young, you don't really care, you don't have experience, you feel invincible, all those things. But as you see, as age increases, your car insurance premium starts to decrease because you're becoming older, more responsible, more experienced. And that's, holding everything else constant, like no DUIs or anything crazy that would make your insurance premium go up. But then, as you start to get older and you start to get a little more senile and your vision, your hearing starts to go a little bit, and heck, maybe you're getting older so you're not really that worried about death and you're just flying down the road and you don't really care and you're like, woohoo, I'm 95 and I don't care if I get hit. This is fun. I don't have much life left in me anyway. Well, then you become more risky again and your car insurance premium goes up. So both of these instances, there's not a consistent increase or decrease in Y as X increases. In this case, it decreases and then it starts to increase at a certain point. Neither one of these are the types of relationships we are going to focus on. We are going to focus on linear relationships, which is the most straightforward and the most commonly assessed. So here's an example of a linear relationship. So the relationship between studying and quiz grades. So for the most part, the more you study, the higher your quiz grade is going to be. And we'll talk about how to interpret this number here in a little bit. But for now, you just know that when you do your scatter plot, if data starts to fit kind of a straight line, even if it's kind of like scattered even more, this is a pretty clear linear relationship. But even if you just see some sort of straight line forming, diagonal, increases in X, in this case, result in or tend to be related to increases in Y. That would be a linear relationship, and you could use Pearson's correlation for that. Here's another example of a linear relationship. And again, we'll talk about what this number means here in a little bit. Well, in this case, it's still a consistent pattern where as X increases, now Y decreases consistently. But there's not like a certain point where it starts to turn up again, and it's no longer linear. So this would also be an example of a linear relationship. More hours of cardio exercise per week, you tend to have less body fat. Linear relationship. So one of the first steps that we will be doing when we calculate correlation coefficients in step 3 is we're going to plot our data. One of the reasons that we want to plot our data is to make sure that it's a linear relationship, and in fact, yes, we can use Pearson's R and it'll be accurate. Another reason that we want to plot our relationships is to anticipate the strength of the relationship and the direction of the relationship. So let's first focus on the direction of the relationship, the second characteristic of relationships. So the direction is told to you by the sign of the correlation coefficient. So you'll either have a positive or a negative correlation. So again, the sign of the correlation, positive or negative, tells you the direction of the relationship. And direction just tells you how the variables are related based on whether scores on the low or high end of one variable's range correspond to the low or the high end of the other variable's range. So if X and Y tend to change in the same direction, so in other words, people who have higher values for X tend to have higher values for Y, and conversely, people who have lower values of X tend to have lower values on Y. That relationship is a positive relationship. And when you calculate the correlation coefficient, or R, because all we're going to be doing is Pearson's correlation, it'll be a positive value. So for example, food intake and weight. You eat more food, you weigh more. You eat less food, you weigh less. Another example, study time and quiz grades that we looked at. The more you study, the higher your grades will tend to be. The less you study, the lower your grades will tend to be. So positive, changing in the same direction. Well, a negative relationship, so if you calculate your correlation coefficient, you get a negative number, then that means that X and Y tend to change in opposite directions. So higher values on X, so people who have higher values on X tend to have lower values on Y. And people who have lower values on X tend to have higher values for Y. So that would be a negative relationship. So the example we looked at earlier, cardio exercise and weight. The more cardio exercise that you partake in, the less, body fat that you have. Another example, class absences and quiz grades. The more class absences that you have, the lower your quiz grades will be. The fewer class absences you have, the higher your quiz grades will be. So those are changing in opposite directions. And when you look at your scatter plot, you can usually tell, unless it's a really weak relationship and dots are just kind of scattered everywhere, which we'll talk about in a little bit, but you can usually anticipate what will be the sign of your correlation coefficient. What is the direction of that relationship? So here's an example of positive direction. So when you plot these out, you'll see an upward slope in your data points. It's going like up the hill here. And that's because you can look at the values and you can look at the picture, the graph, and you can see that as X increases, time studying and hours increases, quiz grades also increase. That's where that upward slope comes into play. And you can look at this here. X is increasing, so is Y. Or if you go from the bottom up, X is decreasing, and so is Y. Positive direction. Negative direction. So in this case, we have an opposite trend here. So as hours of cardio per week increase, percentage of body fat decreases. And you can see that here. Cardio increasing. So this person only exercise or does cardio 0 hours per week. That's me right now, unfortunately. And they're 22% body fat. But then when you go up to somebody who does 4 hours of cardio per week, 15% body fat. So less body fat because of more cardio, or related to more cardio. There's probably other factors going on that are also having an impact on their body fat. For example, people who tend to exercise more probably tend to eat healthier, and that's also going to have an impact as well. So again, correlation doesn't equal causation. You'd be really careful with the words that you use to describe these. And then, going down to the extreme end here, this person is doing 12 hours of cardio per week, good for them, and they're 10% body fat. Negative relationship changing in the opposite direction. And when you look at the correlation coefficient here, this negative relationship, the correlation coefficient is negative, whereas for this positive relationship, it was not negative, it was a positive number. Now, the final characteristics of a relationship that the correlation coefficient tells us about is strength. So strength tells you how consistent the relationship is among variables. And it's denoted by a numerical value of the correlation coefficient. And that numeric value can only range from the absolute value of 0 to 1. And I say absolute value because, yeah, negative values can happen. You can have a value that's less than 1. But if you think about absolute value, it can never be a value that exceeds 1 either negatively or positively. So you can never have a correlation of 1.1 or 1.2 or 1.5 or 5 or 6 or any number that's above the absolute value of 1. Conversely, you can't have any values that are less than negative 1. So you're not going to have a correlation of negative 1.8 or 2 or anything like that. So if you think about this, a strong relationship is a correlation that's closer to the absolute value of 1, be it negative 1 or positive 1. So every time, if you have a strong relationship, every time X increases by 1 point, Y changes by a consistent amount across all study participants. It can be increasing or decreasing as long as it's a consistent increase or decrease. Then you would have a strong relationship. So the strongest possible relationship is when for every change or increase in X, Y changes by the exact amount across study participants. So for example, for each additional hour of study time, it consistently yields 5 more quiz points. Or each additional class absence consistently yields 5 less quiz points. So for instance, somebody who studied for 1 hour would have a 65 on the quiz. Somebody who studied 2 hours would have a 70. Somebody who studied 3 hours would have a 75. And maybe somebody else who studied 3 hours also had a 75. So you see, it's changing by 5 points for each 1 hour increase in studying. That would be like a perfect, strongest relationship you could have possibly have, and it would have a value of 1. But, relatively speaking, as your correlation coefficient gets closer to 1 or a higher value, absolute value, it's a more consistent relationship. Most relationships are not perfect. It's rare to find that. So you know the strength by looking at the numeric value, but you can also predict or figure out what the strength is by looking at the scatter plot. So as the data points become more linear, they fit a straight line a little bit better, you'll see that that is going to be a value that's closer to 1. It's a stronger relationship. So if you go back and look at these two examples where we're looking at direction, these are both really strong relationships as well. And if you look at the numeric value, it's pretty close to 1. It's a really high value. And if you look at the data points, they almost perfectly fit a straight line. If you had a correlation of 1, they would fit a straight line exactly. They'd be identical to a straight line when you plot them out. This one as well. Pretty strong relationship. This value is really close to -1 in this case, but if you just look at the number, not looking at the sign, remember absolute value, it's really close to 1. Even though it's negative, it's still a really strong relationship. Data points almost fit a straight line. And if you look at the numbers, you can see that it's a pretty consistent change in y for each increase in x. On the other end of this, if you have a value for your correlation coefficient that's closer to 0, then you have a less consistent relationship and you have a weaker relationship. So every time x increases by 1 point, y changes by a variable amount across all study participants. So maybe in your study, each additional hour of study time yields a small point increase for some, a large point increase for others, and maybe even a point decrease for some. Maybe they studied so much that they're just burnt out and they can't take it anymore. That would be looking like a weak relationship in your data, because when you plot it out, you'll see that data points are all kind of scattered. It's hard to detect the linear relationship. And if you look at the values in your data set, you'll see that as x increases, there's not a consistent change in y. Now, the strength of your relationship is judged directly related to the criteria that we use for effect size. So R squared is the effect size that I prefer and that we've been using a lot this semester. Well, guess what? R is the square root of R squared. So when we do effect size in correlation, it's real simple. You calculate R in step 3 and you square it, and that's your effect size. Well, the evaluation of effect size and correlation strength are directly related as well. So remember, an R squared effect size of 0.01, we said that was a small effect size, 0.09 was medium, 0.25 was large, 0.50 was very large. Well, if you take the square root of those values, so the square root of 0.01 is 0.10, we'll call that a weak relationship. So if you calculate R and it's around 0.10, we'll call it weak. If you calculate R and it's around 0.3, the square root of 0.09, we'd call that a moderate relationship. If you calculate R and you get 0.50 or around 0.50, that's a strong relationship. And around 0.70 to 1, very strong. Keep in mind, these are absolute values. This is just the numeric value of the correlation coefficient. If you calculated a correlation and you got -0.45, we would still say that's a strong relationship. Remember, strength and direction are not the same thing. Just because the correlation is negative doesn't mean that it's a strong relationship. It can still be strong. So here's an example of a perfect linear relationship, a correlation of 1. And it's positive 1 because, as you see, it's changing in a positive direction. It's an upward slope. And check this out. For each 500 calorie increase across study participants, you see a consistent increase of 50 pounds in their weight. Perfect relationship. And when you plot it out, you see that perfect straight line. Again, this is really, really, really rare in true research situations, but I wanted to show you an example of a perfect linear relationship correlation of 1. Here's an example of a moderate strength relationship. So number of siblings and number of children. And this actually comes from data that I collected from a previous statistics class. I figured they would be a pretty strong relationship. I figured, based on the family dynamics you had growing up, you would tend to imitate that in the future. But that isn't the case. So if you look at the numbers, all these people had one sibling growing up. Some of them had one child, some of them had 2, some of them had 3. So maybe this person enjoyed being an only child and they said, oh yeah, let's go ahead and have just one child. I enjoy being an only child. But again, correlation doesn't equal causation. Maybe just because they had one sibling and one child isn't related. Oh, I have one child because I had one sibling. Maybe it has to do with other factors like the amount of income they have or the age that they were when they started wanting to have children. There's tons of other reasons why you would see that there. Another one, this person had one child or one sibling and had three children. So maybe they hated being an only child and they're like, I want to have lots of siblings for my kids. So they decide to have three kids. Or maybe there's other factors that resulted in that relationship. So when you're looking at, as X increases, Y doesn't really tend to increase or decrease. It kind of goes back and forth. And so when you plot that out, you see more of a spread pattern. But in looking at this, it's moderate strength, but we can tell the direction of the relationship in general. And in general, it tends to be positive. That doesn't mean that everybody who has more siblings has more children, but as a general pattern, you'll see that. If you draw like a circle around your dots, you'll see that it has an upward slope. And then when you look at the correlation coefficient for this data, so what would be calculated in step 3 of your hypothesis test, it fits that moderate criteria. Remember, moderate relationships around 0.30. And you also see that it is a positive moderate relationship. Here's an example of a weak relationship. In this case, it kind of looks like it's a negative relationship, but it's really hard to tell. It's very spread out. And this is actually based on a study that I read about how well your grade in anatomy and physiology predicts how well you do on this thing called the objective structured clinical examination. So nursing students probably know what this is. So this is basically where they have you perform various tasks at these different stations that are related to the work that you do in practice, and then they grade you on a scale sometimes of like pass or fail, or sometimes they're even more refined where they say, not acceptable, acceptable, excellent, superior, all those, different scales. But there was actually a study that looked at this and suggested there really isn't much of a relationship between your grade in anatomy and physiology and how well you do on this exam. They suggested actually that it's academic achievement that is the better predictor of both of these things. But we'll talk about partial correlations and Z variables here in a little bit. So when you look at the data for this, and the reason I chose this example and the reason why they look specifically at anatomy and physiology grade is because a lot of times your employer or even, graduate schools for nursing or even nursing admissions boards for nursing school will specifically look at your anatomy and physiology grade to see how well you did because it's expected that that would predict how well you do in practice. So if you look at the data, look at the numeric values of the data. As X increases, there's really no discernible pattern here, right? This person got a 60 in anatomy and physiology. They also got a 60% passing on the OSCE. This person got a 63, they got an 85. Then this person got a 65 and got a 40. And then when you go down here, this person got an 85 and got a 40. This person got a 65 and got a 40. So that doesn't really make sense. It's like, what's going on there? So looking at the data, you see there's no clear pattern, and then when you plot it out in your scatter plot, which is a much easier way to look at strength, you can see it's all scattered. And then when you calculate the correlation coefficient for this, you'd see that it's a very small number, 0.085. So that is a weak relationship. And it happens to be negative, but it's really hard to tell that by looking at your scatter plot or your data because it is such a weak relationship. It doesn't fit a clear linear pattern. Okay, so now you understand, hopefully, strength and direction of linear relationships and how those are related to the value of the correlation coefficient that you calculate in step 3 of the hypothesis test. But before we get into the hypothesis test, I do want to mention one thing. So not only is the Pearson correlation coefficient only appropriate for linear patterns of data, linear relationships, but it's also only appropriate when you have interval or ratio data. So there's correlation coefficients that you can use when you don't have interval or ratio data, so when you have nominal or ordinal data, but I'm not going to get into those. So just keep in mind the correlation coefficient we're talking about, the Pearson correlation, can only be used when you have a linear relationship and you're measuring interval or ratio data. Okay, now let's move on to the steps of a hypothesis test with a correlation. So step 1, We're still stating our hypothesis, and now we're going back to having one or two-tailed tests. So in ANOVA, we didn't have that, but now we are going to have that. So two-tailed test is just when you expect that there is a relationship. You don't know what kind of relationship. You don't know if it's going to be positive or negative. You just expect that there is some sort of relationship. And a two-tailed test is what's most often used because, as you may remember, it's easier to reject the null hypothesis with a one-tailed test because your critical value is going to be a smaller value. So the default is usually a two-tailed test. We're trying to avoid type 1 error. And in order to justify a one-tailed test, there has to be a lot of previous research supporting that specific expectation that you have. Okay, anyway, two-tailed test, when you see it for practical purposes in the problem, so-and-so thinks that there is a relationship between these two values. Okay? Just relationship, not being specific. Two-tailed test. And what these symbols mean, so the null hypothesis, this represents the population correlation. So the way you could read this out in words is that the true population correlation implied by the sample is 0. So in other words, remember, the closer to 0 your correlation gets, the weaker the relationship. This is essentially saying we don't think there's really a relationship in the population based on our sample. Well, then the alternative, what we typically are expecting, is that there is a relationship. So the true population correlation, this little p here, that's implied by the sample is not 0. So there is some sort of relationship between those two variables, and we would expect to see that in the population as well. Another type of hypothesis that you can have for your hypothesis test in step 1 is a one-tailed test. So if you think that people who have higher values on X tend to have higher values on Y, or people with lower values on X tend to have lower values on Y, you're expecting a positive relationship. And so under the alternative, you're expecting that the population correlation implied by the sample is going to be greater than 0. Remember, positive value greater than 0. If it's not greater than 0, then it's less than or equal to 0 under the null. So it's either a negative relationship, a negative correlation, changing in opposite directions, or there really is no relationship at all, and the correlation is equal to 0. Then you can have a one-tailed test that's negative. So you're expecting a negative relationship or negative correlation. Or people who have higher values on X tend to have lower values on Y. People who have lower values on X tend to have higher values on Y. So the alternative, we're expecting that the population correlation implied by the sample is negative, less than 0. Here, if it's not negative or less than 0, it's positive, greater than 0, or it's equal to 0, no relationship at all. The step 2, you need to determine your critical region. So basically, you're going to find R-crit, which tells you the correlation that you would expect to see just randomly due to chance 5% of the time if your alpha level is 0.05, or 1% of the time if your alpha level is 0.01, and that sets the cutoff for critical or for significant values. So if you calculate a correlation coefficient in step 3 and it falls within that critical region, then you know that the probability of getting that correlation just due to chance, even if there is no relationship between the variables, is less than whatever your alpha level is. All right, so I'll show you the table for R-crit. So you'll see various things here. Just like the t-table, it separates one-tailed and two-tailed, so you don't have to split your alpha level if you have a two-tailed test. So if you're thinking about, one two-tailed test, okay, then you go find your alpha level. Either 0.05 or 0.01 is what we'll be using in this class. Those are the standards. Then you need to find your degrees of freedom. And look, it gives you a nice little hint right here, n minus 2. Be careful, don't count how many numbers are in your data set, count how many rows are in your data set, because remember, each person is measured on X and Y. So you just take n minus 2, find your degrees of freedom, and then go to the corresponding column that matches your tails in your test and your alpha level. So alpha level, one or two-tailed test, and your degrees of freedom. And I even put right here, n is equal to the number of participants or pairs of scores. Then step 3. So this is where the math comes in, all the calculations. So also, prior to calculating R, you want to plot your data points in a scatter plot to estimate that relationship between X and Y. So you want to see, do the points tend to fit a diagonal line? If so, I think that my relationship is going to be pretty strong. I'm going to have a high value for my correlation coefficient. And also, do my data points tend to slope upward or downward? If they tend to slope upward, going uphill, then I expect a positive relationship or positive value for R. If they go downward, I expect a negative relationship or a negative value for R. So it helps you anticipate what value you will get for the correlation, and it also helps you check your work when you do calculate that value for correlation and make sure that you did it correctly. Okay, so in words, the formula for R, or the correlation coefficient, is equal to the degree to which X and Y vary together, or covariability, divided by the degree to which X and Y vary separately, or the variability of each. So the top one is how much do they vary together, how consistent are they, how consistent are the changes between X and Y across everybody in your study, and then the denominator, degree to which X and Y vary separately, that's just looking at the spread of values within X and the spread of values within Y without looking at the relationship between the two. So you might remember when we did ANOVA something similar. So when we did ANOVA, the numerator was the change or the differences between the groups, and then the denominator was the changes within the groups. Well, for R, the numerator, which is also called the sum of products, it's kind of like the sum of squares, but instead of measuring the variability for one variable, it measures the covariability for two variables. And then the denominator, just like in ANOVA, where sum of squares within, you were just combining the sum of squares for each group. That's the same thing that you're doing in the correlation coefficient. You're combining the variability, the separate variability for each group. Remember, in ANOVA, your F statistic would equal 1 if the between groups variability and the within groups variability were the same. Or in other words, there were no differences due to the independent variable, just due to error. Well, now in correlation, you'll get a correlation of 1 or an R of 1 if the degree to which X and Y covary together is equal to the degree to which they vary separately. Then you'll have a perfect correlation. All of those differences can be in X or Y can be tied to the relationship with the other variable. Okay, so breaking down the numeric values for these formulas. So R, sum of products divided by the square root of sum of squares for variable X times sum of squares for variable Y. Remember, I said the sum of products is a lot like sum of squares, except you're looking at both variables at the same time. So here, instead of X squared, we've got X times Y. Keeping in mind, order of operations, each X value times the respective Y value across all people in the study, and then add those values together. So each X times each Y, new column, add those together to get this. Kind of like what you do here, where you just square each X, but instead of that, we're multiplying each X times each Y. Then over here, sum of X times sum of Y. You see parentheses here, so you add up all the numbers for Y and multiply that to what you get when you add up all the numbers for X. And then divide by N, number of pairs of scores, or rows in your data set. And then these two formulas should look extremely familiar. This is the formula for sum of squares that you've always seen. And now this is the formula for sum of squares that you see here. It's just that X is being replaced with Y. So if your R observed, the correlation coefficient that you calculate in step 3, exceeds the critical value of R in the correct direction, then you can reject the null hypothesis. When I say in the correct direction, that's really important if you have a one-tailed test. So you can consult the alternative hypothesis, and the critical value reflects the alternative hypothesis. So if you're expecting a positive correlation, you're only going to have a critical region that's in the high end of the distribution. So that's what I'm saying when I say correct direction. So if your R observed falls in the critical region, or the rejection region, if you want to call it that, then you reject the null hypothesis. And really what you're saying is that we're rejecting the null. We're saying that it's highly unlikely that this observed relationship that we expected is just due to chance. So it's probably due to the fact that there's actually a relationship between those values in the population, or those variables in the population. Okay, so if you reject the null hypothesis, if you have a two-tailed situation, then you could say results suggest that there's a significant relationship between whatever x is and whatever y is. Be careful. Do not say X causes Y. Don't even allude to that in your conclusion because, again, correlation doesn't equal causation. So there's a relationship between the two. If it's a one-tailed test and you reject the null, then you could say results suggest that there is a significant positive or negative, whichever one you're expecting, relationship between whatever X is and whatever Y is. Thus, people with more or less X tend to have more or less Y, depending on if it was a positive or a negative relationship that you were looking at. Again, not X causes Y. That's inaccurate. Just because there's a relationship doesn't mean that one thing causes the other. Also, as always, your conclusion should mention the independent variable and the dependent variable. Don't put X and Y. Put what X was actually related to. What is the X variable and what is the Y variable? And then you want to include the word significant. Also, if it's a one-tailed test, you want to be specific. Mention if it's positive or negative. Okay, so now that I've gone over the conceptual pieces of correlation and I have gone over the steps of a hypothesis test, let's actually go through all the steps of a hypothesis test. Okay, so let's go ahead and start with step 1. And step 1 is based on the context of the problem and what the researcher expects. So if we look at this, a researcher wants to examine the relationship between marital satisfaction and overtime hours. Individuals are asked to rate their marriage satisfaction on a scale of 1 to 10, so 1 being not at all satisfied, 10 being extremely satisfied. They also record the number of overtime hours they worked in the past month. So we're looking at this data to see if there's a significant relationship between marital satisfaction and overtime hours, and if there is, what's the size of the effect? Keyword, relationship. It doesn't say positive or negative relationship. It doesn't even say we want to see if those who work more overtime hours have less marital satisfaction or tend to have less marital satisfaction or anything like that. We're just saying, is there a relationship? So that tells me for step 1, we're looking at a two-tailed test. So my null is going to be that the population correlation implied by my sample is equal to 0. No relationship. My alternative is that the population correlation implied by my sample does not equal 0. There is some relationship. Then in step 2, I need to find my R critical. And I know if I'm drawing out my critical region, I can go ahead and put 0 here, meaning no relationship between the two variables. And then as your values get farther away from 0, that means there's a stronger relationship between the variables. Also keep in mind that the cutoff for this is -1 and +1. Because remember, the strongest relationship you can possibly have is the absolute value of 1. Okay, two-tailed test. Let me go ahead and draw my two tails so that I'll remember when I find my value to include that positive or negative in front of it. All right, R crit. Alpha level is 0.05. Degrees of freedom, so n minus 2 is equal to, well, 1, 2, 3, 4, 5 people. 1, 2, 3, 4, 5. 5 minus 2 is 3. And alpha is 0.05 and 2 tails. All right. So let's check our table and see what our critical value would be with degrees of freedom 3, alpha level 0.05, two-tailed test. Okay. Two-tailed test, alpha level of 0.05, and degrees of freedom of 3. I'm looking at 0.878. Two-tailed test, 0.05 alpha level, degrees of freedom 3, 0.878. Not just 0.878, but positive or negative 0.878. Whoa, what happened there? Okay. So now moving on to step 3, and I'm going to go ahead and do that on another page here, just to make some room. All right, step 3. So I already did the calculations for x times y and x squared and y squared here. I'll walk you through it really quickly. And I know that I need to do this for my sum of squares and my sum of products that I'll get to here in a minute. So x times y, xy, 4 times 8, that gives me 32. 4 times 9, see that here, gives you 36 all the way down. Add those together, you get sum of xy. Multiplication comes before summation. X squared, so each x value squared. 4 times 4, 4 times 4, 16 times 16, 8 times 8, 24 times 24. Add those together, sum of x squared. And then y squared, all of the y's squared, and then add those together to get sum of y squared. Okay, so let's go ahead and first off, let's write down the final formula that we're going to need. And the formula for r, again, is sum of products divided by the square root of the sum of squares for variable x times the sum of squares for variable y. So, sum of products divided by square root of sum of squares x times sum of squares y. All right. Well, I'm looking at this and I know I need 3 formulas. I need the formula for sum of products, sum of squares x, and sum of squares y. So, sum of products is equal to sum of x times y minus sum of x times the sum of y divided by sample size. And because this has already been done, and you'll be doing this on your own in the knowledge check, I got my sum of xy, sum of x, sum of y, boom, good. No more formulas there. Now, sum of squares x. This should be a formula that you know pretty well. Sum of x quantity squared divided by n. And I'm looking at this, and I already have my sum of x squared, boom. Sum of x, boom. I know my n, done. Sum of squares y. Sum of y squared minus sum of y quantity squared divided by n. I've got my sum of y squared here and my sum of y here, and I know that my n is 5. So I'm done writing down formulas. All right, let's start with the bottom and work our way up. So sum of y squared is 201 minus sum of y, 29 squared divided by 5. So this becomes 201 minus 841 divided by 5, which becomes 201 minus, so 841 divided by 5 gives you 168.2. And your final value for the sum of squares y is 32.8. Sum of squares y. All right. Again, write your formulas, write each step, and then highlight your final answers so that when you go to plug in your thing that you need for r, you can find it easily. All right. Sum of x squared, found that to be 928, minus sum of x, 56 squared, divided by 5, our n. This becomes 928 minus 56 squared is 3,136 divided by 5. This becomes 928 minus, well, 3,136 divided by 5 gives me 627.2. And then that final calculation is 300.8. 0.8. That's my sum of squares, x. Perfect. Sum of products. Sum of xy, 228, minus sum of x, 56, times the sum of y, 29, divided by 5. This becomes 228 minus 56 times 29 is 1,624 divided by 5. This becomes 228 minus 324.8 and you end up with negative 96.8. Now, one thing I want to mention. Your sum of squares x and sum of squares y will never be negative. There's not going to be negative variability. But your sum of products can be negative. It's all about the covariability. Well, if y tends to decrease as x increases, then you're going to have a negative sum of products. So the negative or positive sign of your correlation is really driven by the covariability or the sum of products. So now let's plug in all the numbers that we just found. So negative 96.8 divided by the square root of 300.8 times 32.8 equals, okay, negative 96.8 divided by the square root. So the square root of, 300.8 times 32.8 gives you 9,866.24. 9,866.24. This becomes negative 96.8 divided by, so the square root of 9,866.24 is 99.3289. And you end up with a final value of negative 0.975. Negative 0.975 is R. Now, I'm a bit of a hypocrite because I kept saying you need to draw your scatter plot before you do your calculations, but you can draw it afterwards as well, just to check your work. So let's go ahead and do that. All right. Don't criticize my beautiful art here. So we've got x-axis is overtime hours, and then the y-axis is marital satisfaction. All right. Overtime hours ranges from 4 to 24, so I'm just going to go count by 4. 0, 4, 8, 12, 16, 20, 24. And marital satisfaction ranges from 2 to 9, so let's just do 0, 2, 4, 6, 8, and 10. Okay, so the first person worked 4 overtime hours and had a marital satisfaction of 8. 4 and 8, right about here. Next person, overtime hours of 4, marital satisfaction of 9. So right about here. Next person, 16 overtime hours and marital satisfaction of 4. So right about here. Fourth person, 8 overtime hours, marital satisfaction of 6. So right about here. And then the last person, 24 overtime hours and a marital satisfaction of 2. Right about here. This is a clear, strong negative relationship. And that is awesome because that matches what we got for our correlation coefficient here. It's strong and it's negative. Now keep in mind, sometimes you can have a strong relationship that's actually not a significant relationship if your sample size is really, really small. So let's go back and see if this is significant. Keeping in mind negative 0.975 is the correlation coefficient. So remember our critical value of plus or minus 0.878, so negative 0.878, positive 0.878. And remember we calculated R and we found that it was negative 0.975. Well, negative 0.975, so our R observed from step 3, negative 0.975. That is way out here. So this relationship is strong enough to reject the null hypothesis in step 4. So reject that null hypothesis. So we're rejecting this notion that there is no relationship in the population. And then results suggest there's a significant relationship between marital satisfaction and overtime hours. So results suggest, and I'm going to be lazy significant relationship between marital satisfaction and overtime hours. Okay, well let's go ahead and find the effect size, R squared. So what proportion of the differences in marital satisfaction can be attributed to the relationship between overtime hours and marital satisfaction? So R squared is literally equal to squaring R. So negative 0.975, the R that you calculated, squared. And when you do that math, you end up with 0.951. 0.951. That is our effect size. So, based on just looking at these two variables alone, without looking at any other variables that may be related to both, we can say, based on the study, that 95.1% variability in marital satisfaction is predicted by the relationship between marital satisfaction and overtime. That's crazy large effect size. Let's go ahead and do another example. So in this one, Christine is an IO psychologist who wants to study the relationship between experiencing workplace psychological aggression from coworkers and how individual employees feel about their own effectiveness on the job, so self-efficacy. And she suspects that more workplace psychological aggression experiences tend to be related to significantly lower levels of self-efficacy. So just looking at that, some key words here. More workplace psychological aggression tend to be related to significantly lower levels of self-efficacy. So think about it for a second. Are we expecting just a relationship, a positive relationship, or a negative relationship? So hopefully you've come to the conclusion that we're looking at a negative relationship. As X increases, workplace aggression, Y tends to decrease, self-efficacy. And I just put this here to give you some context of how one of these things may be measured. Keep in mind, though, that in survey studies, we usually include multiple items to measure the same construct, but just to keep it simple, I only put one item for self-efficacy and then one item that could be used in a survey to measure workplace psychological aggression. And then here's our data. So this first person rated themselves as experiencing rude, disrespectful, and intimidating treatment from coworkers or management as a most times, and they rated their self-efficacy saying that they're somewhat confident in their capability to organize and execute the courses of action required to manage prospective situations in their job. So we've got 1, 2, 3, 4, 5, 6, 7 people. Here's their ratings on aggression and self-efficacy. So let's go ahead and do all the steps of a hypothesis test. Okay, so let's go ahead and start with step 1. So step 1. I'm going to go ahead and state my alternative first because with the one-tailed test, it's a little bit easier to do it that way. So if we're expecting a negative relationship, more aggression tends to be related to less self-efficacy, then our population correlation implied by our sample would be less than 0, negative. And other than all, if it's not less than 0, then it's going to be positive or equal to 0. Greater than or equal to 0. Okay, step 2. R crit. Well, alpha level is 0.05. Degrees of freedom is equal to n minus 2. We have 1, 2, 3, 4, 5, 6, 7 people. So 7 minus 2 is equal to 5 degrees of freedom. And we have a one-tailed test on the negative side. So if I draw my critical region before I find the actual value, this is 0 still. I'm only looking down here, the low end of the distribution. So let's go ahead and find what R crit is. Okay, so we're looking at a one-tailed test, alpha level of 0.05, and we just found that our degrees of freedom is 5. So 5 over here, 0.669 is our critical value. 0.669. 0.669. And because I drew my picture, I'm not going to forget that's a negative 0.669. So let's go ahead and put that there. Okay. So let's go ahead and do step 3 on the next page. So again, I've done all the preliminary calculations already just to make it look neat and to save some room. Keep in mind that in the knowledge check, you'll just be given this and you need to know how to calculate all of these things. Okay, so let's go ahead and write down all the formulas that we need to calculate our correlation. So R is equal to sum of products divided by the square root of sum of squares x times sum of squares y. Our sum of products is equal to the sum of each x multiplied by each y and added together, minus the sum of x multiplied by the sum of y divided by the sample size. Sum of squares x is equal to all the x values squared and added together, minus all the x values added together and then that final value squared divided by sample size. And sum of squares y, sum of all the y scores squared and added together, minus all the y scores added together and that entire value squared divided by sample size. Okay. Sum of y squared is right here. It's 101. Sum of y is 23. Square that divided by 7. It's our sample size. This becomes 101 minus, so 23 squared is equal to 529. And then divided by 7. This is equal to 101 minus, so 529 divided by 7 gives you 75.5714. 0.5714. And 101 minus 75.5714 is equal to 25.429. It's 25.429. That is our sum of squares y. So the overall measure of variability in our y variable, or self-efficacy. Okay, x squared, sum of x squared, 92. And sum of x was 22, so square that. Divided by 7. All right, this becomes 92 minus, well, 22 squared gives you 484. And then 92 minus 484 divided by 7 gives you 69.1429. 69.1429. And you end up with the sum of squares x of 22.857. 22.857. All right. Now let's move on to the sum of products. So sum of xy, each x times each y and add those together. Get 52 in this case. Sum of x was 22, sum of y was 23, and there's 7 people in the study. This becomes 52 minus, well, 22 times 23 gives you 506. 506 divided by 7 becomes 52 minus, well, 506 divided by 7 gives you 72.2857. 72.2857. And you end up with a final value for sum of products of negative 20.286. Negative 20.286 equals sum of products. All right. I forgot to do my scatter plot again. I just get so excited by calculations. That's what I jump to first. But that's okay. We'll do it next. All right. Found my sum of products. Negative 20.286 divided by the square root of my sum of squares x, 22.857, times my sum of squares y, 25.429. This becomes 20.286 divided by the square root, so 22.857 times 25.429 gives me 581.2307. 581.2307. 2307. So 20.286. Oh, negative. Don't forget your negative. So the square root of 581.2307 is 24.1087. 24.1087. And you end up with a correlation of negative 0.841. So, just like the last one, actually, strong and negative. So let's go ahead and draw our scatter plot to make sure that that comports with what we just calculated. Okay. X-axis, aggression. Y-axis, self-efficacy. Abbreviate there. So aggression in this case ranges from 1 to 6. So 1, 2, 3, 4, 5, 6. And then self-efficacy from 1 to 6 as well. 1, 2, 3, 4, 5, and 6. All right, first person, 5 on aggression, 2 on self-efficacy. Right about here. Next person, 1 on aggression, 5 on self-efficacy. Next person, 2 on aggression, 3 on self-efficacy. And the next person, 4 on aggression, 1 on self-efficacy. And the next person, 6 on aggression, 1 on self-efficacy. And then 3 on aggression, 5 on self-efficacy. And then 1 on aggression, 6 on self-efficacy. All right. So you can see that this one isn't as strong as the previous one. The data points don't fit a straight line perfectly. But you can still, if you draw a circle around it, you can see the circle's pretty narrow, meaning that it's a strongish relationship, and it has a downward slope. So, negative, strong, matches our actual value here, which is great. So now, in step 4, does that value, that correlation coefficient that we calculated, that R observed from step 3, and remember, it was negative 0.841. Negative 0.841 totally falls in the critical region. So we are going to reject the null hypothesis. And the results suggest that, I'm going to be lazy again. So you could say people who have more workplace psychological aggression experiences tend to have significantly lower levels of self-efficacy. That's more of like a kind of plain English definition. Or you could say there is a significant negative correlation or relationship between aggression and self-efficacy. And what's the effect size of this? Well, we found R to be negative 0.841, so we just square that. And negative 0.841 squared is 0.707. And this is a large effect. And just based on this study, we could say that 70.7% of all the differences in self-efficacy are related to the relationship between aggression and self-efficacy. Okay. So now that I've shown you how to use correlation and explained to you how to interpret it, now let's talk about why correlation is probably a flawed strategy at best. And it's not flawed because of the statistical analysis, it's flawed because of the type of study that leads us to do a correlational analysis. So remember, with correlation, most times those correlational studies are not true experiments. They do not involve the manipulation of conditions or control over other factors which may influence the relationship between the two observed variables, between x and y. Correlational studies are just aimed at describing the relationship between two naturally occurring variables, and it's typically through self-report surveys. So nothing's being manipulated. You're not really able to control for other influential factors that may have an impact on your dependent variable, and there's tons of problems inherent in asking people to report through self-report. It's not a true experiment that leads to a correlation analysis. Correlation does not equal causation. Remember, a true experiment is the only way to make causal inference, and correlation is far from a true experiment. A significant correlation only tells you that two variables are related, not which variables cause which, or even if there's a cause-effect relationship at all. So sometimes it can be unclear which variable in your relationship is the independent variable and which is the dependent variable. So in that case, the direction of causality is unclear, if there's even causality at all. You don't necessarily know which one came first. So these pictures represent how correlational relationships are depicted in graphical form. This little double-sided arrow implies we don't know for sure which one came first. So think about our example from before, looking at the relationship between overtime hours and marital satisfaction. So in the hypothesis that we did in the example, we assumed that overtime hours was predicting marital satisfaction in some way. And we actually found that those who tend to work more overtime hours tend to have less marital satisfaction. Well, think about how maybe there could be a positive relationship between overtime hours and marital satisfaction. Think about how that could play out. I'll give you some time. So maybe those who work more overtime hours tend to have more marital satisfaction. Well, that could be because maybe they don't really like their spouse very much and they're away from them a lot. So they're working more, they're not around each other. Absence makes the heart grow fonder. They are more satisfied. Or maybe they're making more money because they're working more overtime. So when they do get to spend time together, they get to go out and do expensive fun things. Or, another host of reasons why that relationship could be there. Now I want you to think about how maybe marital satisfaction could be the independent variable in this relationship. Okay, so maybe those people, if there was a negative relationship there, maybe the people who are more satisfied with their marriage work less overtime hours because maybe they want to spend a lot more time with their spouse. Or maybe those who are less satisfied with their marriage work more overtime hours because they don't want to be home. They don't want to be around their spouse. So that would be an example of a positive relationship. Okay, the other one that I want to talk about, this confusion between maybe something is the independent variable or the dependent variable, we don't really know. Job satisfaction and performance. So there's a lot of research in IO psychology looking at this relationship. Well, it could be that job satisfaction predicts performance, and they typically do find a positive relationship. So maybe it's the fact that those who are more satisfied tend to have higher levels of performance. They're more satisfied. Maybe they're more engaged in their work. Maybe they're more motivated. Or it could go the other way around. Maybe those who are good at their job and have high levels of performance tend to be more satisfied as well. So you can see here how sometimes it can be unclear which variable in this relationship is the independent variable and which one is the dependent variable. Now, in true experiments, you know which one's the dependent variable. It's the one that's being measured. And if there are differences between groups, especially in like an ANOVA type situation where you have a control group and then multiple research groups, and you control for everything else other than the independent variable, we can be pretty confident that it is the independent variable, the thing you manipulated, that's having an impact on those scores on the dependent variable. But that's not the case in correlation. Another thing I want to talk about is the partial correlation type of situation. Or in other words, you may observe a really strong relationship between two variables, but that observed relationship may actually be the result of the fact that A variable or several variables are related to both x and y, and that's artificially inflating that observed relationship. So the first two that I'm going to talk about are kind of silly examples, and then I'm going to talk about two a little more serious examples. So the first one, there's a really high, so strong positive correlation between shoe size and reading ability. So those who have larger shoe size tend to have better reading ability, and those who have smaller shoe size tend to have less reading ability. So in the face of this, if you weren't a critical consumer of research, you'd be like, oh man, if I've got big feet, I'm an awesome reader. That's great. Cool. Well, think about it. What do you think could be related to both shoe size and reading ability that may artificially inflate that relationship, that strong correlation? So, age, right? So, people who are older tend to have a larger shoe size and also tend to have stronger reading ability. Conversely, those who are younger tend to have smaller shoe size and probably less reading ability. Okay, next one. This is a classic example of misleading correlations. So research has suggested that there is a strong positive correlation between ice cream sales and the crime rate. 0.75 is a strong positive correlation. So it could be that, people eat ice cream and they get really pumped and they go out and they commit some crimes. That ice cream really influenced their crime committing desire. I don't know. Or maybe it goes the other way around, and maybe after somebody commits a crime, they really want some ice cream. Probably not the case. So, what do you think is a third or a z? We're calling, our independent variable x and our dependent variable y, and then z is the letter, the variable that we assign to this other thing that's driving this relationship. So, what could be our z variable in the ice cream sales crime rate example? So temperature may be an influence, right? So, as it gets hotter, ice cream sales go up, and as it gets hotter, the crime rate tends to increase, especially in cities where the winters are brutal and nobody even has the motivation to go outside and commit a crime in the ice. Okay. Also, as temperature gets colder, ice cream sales go down and crime rate decreases. So you can see how that third variable is what's influencing that observed relationship between ice cream sales and crime rate. So here's another example that's pretty relevant to you guys. So there's a big, big push for this 15 to complete, I think is what it's called, where they're really encouraging college students to take 15 credit hours a semester because research suggests that those who take 15 credit hours a semester have a far, far better college completion rate. So they're more likely to complete college if they're taking 15 credit hours a semester. So you look at this strong positive relationship here. Well, there could be a number of other factors that are related to both of these that could artificially inflate that relationship. So instead of just saying, okay, everybody needs to take 15 credit hours a semester so that you'll be more likely to complete college, well, maybe those people who can take 15 credit hours a semester also are only going to school and they're not working and they don't have kids and they're able to devote all the time that it takes to successfully complete 15 credit hours each semester. So they don't have any other barriers that would prevent them from completing college as well. If I have a child and I'm in college, it's going to be really difficult for me to take 15 credit hours. Also, if I have a child and that child gets really sick and requires expensive medical care, chances are I'm not going to be able to afford to complete college in the first place. So there's a variety of reasons why that relationship could be artificially inflated and that you may not want to take that result at face value and say, okay, everybody needs to take these credit hours because it's related to college completion. Different people have different circumstances. Okay, another example. There is a strong negative relationship between yearly income and number of children. So you can't just say, okay, well, that must mean that those who are poorer tend to have more children, and those who have more money tend to have fewer children. Well, that doesn't really make sense because, you would think that if you make more, you can afford more children, so you would have more. If you make less, you may try to restrict how many children you have because you can't afford to have them. There's a third variable that is related to both of these that's probably artificially inflating this relationship. So think about what that third variable could be, something that's related to yearly income and number of children. So how about education? How many years of college did you complete? So those who complete more college, more educated, tend to have a higher income. They also tend to have fewer children. They put their education first, made it a priority, and therefore, for the most part, they had to wait longer to have children. So, if you wait longer to have children, chances are you're going to have fewer children. Or maybe you waited so long, you spent 12 years in medical school, and then you tried to get pregnant, and it was difficult to get pregnant, so you only had a couple of kids if you were lucky enough to have a couple of kids. So that third variable, education, could be the reason why you see that observed relationship between yearly income and number of children. So there's something that's called a partial correlation, which is a calculation that allows you to look at the relationship between x and y while controlling for that z variable, that third variable that may be related to both of those variables. Partial correlations. Now keep in mind this may look like a scary formula, but in all cases I'm going to give you these values here. I'll tell you what the relationship, the correlation coefficient between x and y is, or in this case, shoe size and reading ability. 0.80 is the correlation there. I'll give you the correlation coefficient between x and z, so your independent variable and then that third variable that's related to both. So in this case, x and z, shoe size and age, correlation of 0.90. And I'll also give you the correlation coefficient for y and z. So in this case, reading ability and age, 0.85. So let's go ahead and work through the calculations for the partial correlation. And the way that this works is that you end up with a correlation coefficient between x and y after controlling for z. And if what you calculate for your partial correlation is much smaller than what you calculated originally for the original correlation between x and y, then you can conclude that z is artificially inflating that relationship. Or if it becomes non-significant, so if you look at this and it's not significant anymore, then you can say that z is the entire reason for the relationship, the observed relationship between x and y. So in other words, if we calculate this and we get something that's substantially below 0.80, then we know that z is probably the reason that we see this relationship. Okay, so let's work through this calculation. So rxy is equal to 0.80 minus rxz, which is 0.90, times ryz, I'm just going to put a little star here for multiplication, which is 0.85. Okay, divide that by the square root of 1 minus, so rxz squared, so 0.90 squared, times 1 minus ryz squared, 1 minus 0.85 squared. So then this becomes 0.80 minus, so 0.90 times 0.85 is 0.765. Divide that by the square root of 1 minus, so 0.90 squared gives you 0.81. And then 1 minus 0.85 squared, so 0.85 squared becomes 0.7225. Okay, well 0.80 minus 0.765 is 0.035. And 1 minus 0.81 gives you 0.19. And 1 minus 0.7225 gives you 0.2775. And let's just keep our 0.035 in the numerator. We're done with the numerator. 0.19 times 0.2775 gives you 0.0527. Don't forget your square root. So 0.035 divided by the square root of 0.0527 is 0.2296. And your final value for your partial correlation is 0.152. R between X and Y after controlling for the relationship between Z and Y and Z and X. Or in other words, this is the correlation coefficient for the relationship between shoe size and reading ability after you control for the relationship between age and shoe size and the relationship between age and reading ability. So in this case, you could conclude that age explains most of the relationship between shoe size and reading ability. That correlation decreased quite a bit. It went from pretty strong to not so strong. All right. Let's do another example. So looking at that relationship between yearly income and number of children, after controlling for the fact that those who go to school longer tend to have fewer children and tend to have a higher income. All right. So R, X, Y, Z. So R, X, Y, the relationship between our independent and dependent variable in this case, negative 0.60 minus, minus RXZ, which is 0.85, times RYZ, which is negative 0.70. Divide that by the square root of 1 minus R squared XZ, so RXZ is 0.85, I'm going to square that. And then 1 minus RYZ squared, RYZ is 0.70 squared. I'm not even going to put the negative there because I know that a negative times a negative becomes a positive, so the negative will disappear anyway. All right, so then this becomes negative 0.60 minus, so 0.85 times negative 0.70 is negative 0.595, negative 0.595. Okay, divided by the square root. So 0.85 squared is 0.7225. So 1 minus 0.7225 times 0.70 squared. So 1 minus 0.70 squared becomes 1 minus 0.49. Okay, next step. So when you have a negative and you're subtracting a negative, this essentially becomes a positive. So if we rewrite this, it's like negative 0.60 plus 0.595 divided by the square root. So 1 minus 0.7225 is 0.2775. 1 minus 0.49 is 0.51. Negative 0.60 plus 0.595 becomes 0.005 divided by the square root of 0.2775 times 0.51, 0.1415. Don't forget your square root. And this becomes 0.005 divided by 0.3762. And you end up with a partial correlation of 0.013. So that is the correlation coefficient for the relationship between income and number of children after controlling for the fact that both are related to years of education. So it actually became positive. So it's suggesting that, as your income increases, you tend to actually have more children, but it's such a weak relationship that I wouldn't even go so far as to make that conclusion. I would say there's pretty much no relationship between income and number of children after you control for years of education. So you could say there's a very weak relationship between income and the number of children after you control for education. Okay. So another thing that I want to talk about are outliers. So outliers are just when you have one or two extreme scores that drastically alter the correlation between X and Y. So remember, the mean can be biased by an outlier. Like if you have a mean, or if you have an outlier, an extremely high score in your data set, well, your mean is going to be higher and it's going to not reflect the true trend in your data. Well, the same thing happens with correlation. So remember before when we looked at this moderate strength relationship between number of children and number of siblings. And again, correlation was 0.283, moderate positive. Look what happens when you add one person that had 10 siblings growing up and had 10 children. Well, if you go back, if you drew a circle around this data, it's a pretty wide circle and you can kind of tell, yeah, it's positive. But if you do that here, if you drew a circle around this data, it becomes a lot more narrow because of this outlier. So closer to fitting a straight line, so stronger, and it's clearly a positive relationship. And when you calculate the correlation coefficient, just by adding this one person, it goes from a 0.283 to a 0.713. So it goes from moderate to strong, just by adding one person to your data set. So again, correlation doesn't equal causation. For one, because you don't know what's the independent variable and dependent variable if you didn't manipulate anything. You don't know if there's other variables that are contributing to the observed relationship between two variables. And you don't know if maybe there's just a couple of extreme people in the sample that completely change the nature of the correlation coefficient. Another problem with correlation, why correlation doesn't equal causation, is restriction of range. So restriction of range is something that happens when you don't really have the full range of all the values for X and Y that you would see in the population at large. So if you're only looking at limited range of values for the variables, you can actually underestimate the true relationship between two variables. So if you remember when we were looking at the relationship between your anatomy and physiology grade and the percentage of passing stations on the objective structured clinical examination, you can clearly see a restriction of range here. This represents the percentage of passing stations, the percentage of anatomy and physiology, so you know that's going to range from 0 to 100. But there's a problem here. Chances are those individuals who did really poorly on anatomy and physiology probably didn't even make it to the point where they would be taking the OSCE. Maybe they failed out of school, or maybe they didn't even get the job because part of getting the job or getting into nursing school or whatever, getting to medical school, requires you to do well in anatomy and physiology. So we have restriction of range. We have no access to what the passing number of or percentage of passing stations would have been for people with a low anatomy and physiology grade because they never even got to that point. So we don't have any data for these people here. Well, again, this was a weak negative relationship, and that could be underestimating the true relationship because we don't have anybody with a really low grade in anatomy and physiology. Everybody who got to go on and take this exam passed anatomy and physiology. Well, look what happens if we get some data, perhaps, for people who did really poorly in anatomy and physiology, so they didn't pass. And then we had their data on the passing stations. So maybe we did some sort of thing where we tested these people even though they didn't make the cut and they never got to be a medical professional, and we looked to see how many they would pass based on their anatomy and physiology grade. Or maybe we're just really, really desperate for medical professionals and we just stop looking at anatomy and physiology to determine if they can become a medical professional. Well, just by adding these, let's see, 5 to this data set, if you drew a circle around this, it would look a lot narrower, be a stronger, more linear relationship. And if you calculate this out, it becomes a strong relationship and it actually becomes a positive correlation. So restriction of range is a serious problem. In my field of study, it's a major problem because a lot of times you want to see if there's a relationship between a selection test that you're going to use to hire employees and their performance. Well, if you use, a lot of people do something called a concurrent design where they'll give the selection test to the current employees and then compare that to their performance evaluation score. Well, you have restriction of range on performance because chances are the people who are really low performers got fired or quit, and you don't have access to their data on performance and what they would have scored on the selection test. So, restriction of range is a serious problem, and it's definitely something that people should consider when they're doing research. Well, I hope that this helped you understand correlation. It's probably the most commonly referred to statistical analysis, so understanding it will be really beneficial for you even if you don't go on to do research. More importantly, understanding the limitations of it are one of the main things I want you to take away from this class. It's important for you to understand that if there's not a true experiment and they're just looking at a correlational study, you cannot infer causation. Granted, correlational studies aren't worthless because the culmination of lots of studies and replication can help inform true experiments that can happen later because you don't want to waste time and energy doing all these true experiments on something that's not even related. Yep. All right, guys. Bye.